2, 1, here we go. Yet another 2070 online video. And today we're going to talk about a very famous type of problem, one that you may have heard of or have some experience with. Alright, so let's, before we get into the titular problem, let's sort of set things up by asking a pretty straightforward question. Solve Ax equals b, here where A is this 2 by 3 matrix and B here is this 3 by 1. So note, by the sizing of everything, we know that X here would have to be a element of R2 in order for the dimensions here to add up correctly, right? We have 3 rows and 2 columns, so we have a 3 by 2. And then an element of R3, so our X would have to be an element out of R2 in order for this to work. Now, before we even go all guns blazing into this, we already are a little suspicious because, well, alright, I got 3 rows, 2 columns. If I think about that, that means I have 3 equations, but 2 unknowns, so I may not actually be able to solve this. I may not actually be able to find an X that makes this work, and indeed, that is what happens if we augment the matrix A with the vector B, and then find the reduced echelon form. You will find this, and hey, look at this. This bottom row gives me a faulty equation. This would tell me that 0 is equal to 1, and thus the system is inconsistent, and so it has no solution. Or does it? Now, let's use all of the stuff we have just built up over the past few videos and see if maybe we can actually get an answer here, even though we know we technically can't. Indeed, if I orthogonally project my vector b into the column space, the column space consists of all vectors that look like a times x. Well, if I orthogonally project b into that, I'll get some a times, let's call it x hat. I don't necessarily know what this is. And what do we remember about the orthogonal projection? We remember that it makes the distance between the vector and its projection as small as possible. Now note, again, the column space is indeed a subspace. So hey, look at this. I may not be able to get ax to equal b, but it looks like I'll always be able to make the distance between ax and b as small as possible. So in other words, this is the best possible solution we can find in terms of the distance between the vector and a times x. And finding x hat here is called the least squares problem. Hey, the name. Right, and the name for that is that the length, as we know, is the square root of a sum of squares. So, hey, you're trying to make a sum of squares as small as possible. Hence, least squares as the name. Alright, beautiful. So, as we see, ax equals b may not have an answer, but I can make ax minus b as small as possible. Now, that may actually equal 0, and that'd be great, but as we just saw, it's possible it doesn't equal 0, but we can make that value, and note here in terms of the length, the usual Euclidean distance, as small as possible. Alright, so that's pretty cool, but question, how do I actually find x hat? Alright, well, if we were to break it down, what would the steps be, right? Let's think about everything we just built up here. Well, in order to get the projection, I need some orthogonal basis, and to make an orthogonal basis, well, I need a basis, and then apply the Gram-Schmidt. So what I'd have to do is, well, find a basis for a column space, which we know how to do. You get the ref, and you find the pivot columns. That would give you the basis. Then you have the basis, so we hit it with Gram-Schmidt. You get your orthogonal basis. Now you have your orthogonal basis. The projection can be computed by computing the associated dot products. Then equipped with that, we now know what x hat, we now know what y needs to be, the value that equals a times x, and then to solve for x hat, you then would solve that equation, which then you would just do ref. And Oh boy, that sounds like a lot of work, right? So you would take your matrix, get a basis for its column space, Gram-Schmidt that, then compute the projection, and then solve y equals ax hat. Okay, fortunately there is a shortcut, because if we're a little clever about all of these tools we've established, we actually can quickly set up one equation to solve rather than going through all of that rigmarole. Now, be my guest, go ahead and do that computation, go crazy, but there's an easier way. So take a matrix, let W be its column space, again, it's a subspace, let B be a vector. Now, let's note that our vector B can be rewritten as its projection plus some defect, and the projection, since it lives in the column space, has to be our ax hat. Alright, now what's this defect term z? Well, it's literally just solve this equation for z. And note, it's B minus its projection, and as we pointed out, that has to live in the orthogonal complement of our subspace. And hey, our subspace in this case is the column space, and hey, didn't we point out that the complement of this just so happens to be the null space of A transpose, the last of the fundamental subspaces for a matrix. So hey, this quantity is in A transpose, and if we just the null space of A transpose, and if we plug that in, well, you'll get 0 is equal to A transpose Z. Okay, well, we know that Z here would have to be B minus AX hat, distribute the A transpose, and now turn that into a single equation. There we go. If you want to solve for X hat, these are the equations you actually need to solve. Beautiful. So you don't need to go through that whole process I just described. You can, but this is obviously much quicker. So if you want to get the least squares solution to your AX equals B, this is what you would do. And it's worth noting that these have a name. These are usually referred to as the normal equations for x hat. Alright, so let's actually put this to work now that we have it. So, return to this equation we started with. We know this has no traditional solution. There is no x, so that ax equals b here. However, we can always find an x hat, so that A transpose AX hat is equal to A transpose B. And we know that that is going to minimize the distance between B and A times X. So giving us the best possible approximation of a solution. Alright, so compute A transpose A, compute A transpose B, set them equal to each other, and solve for X, and boom! Done. We did it. We have solved the least squares problem for this particular matrix and vector. Hooray! So we did it. Alright. Now, obviously there are ins, outs, and what have yous here, and the big one for least squares that's worth mentioning is that they are not necessarily going to be unique. So, right, instead of trying to actually solve ax equals b, we're trying to minimize ax minus b's length. And it turns out that there are multiple vectors that are potentially going to work. So for example, let's consider the following. So here I have a 4x3 matrix. And again, if we were to think about this, I have 3 unknowns and 4 equations. So probably not going to get an answer. Alright, well, the least squares solution associated with this would be the following. I've already computed A transpose A on the left and A transpose B on the right. Okay, and if you were to go ahead and get the ref of the augmented matrix, it's that, and we see a big fat row of zeros at the bottom, so we know we have some free variables. And in particular, if you were to work it out, here you would get your least square solutions of the following form, and we'll see that, yep, they're not necessarily unique, but we can, of course, get, equations for all possible ones. So, right, you kind of give up on actually solving ax equals b, I'm going to look for ax minus b's smallest possible length, and it turns out that sometimes there's infinitely many vectors that work. And then here, right, you may be interested in like, oh, can I always find them with like all positive values, or like component 3 is always positive or component 2 is always positive. Depending on the kind of problem you're working on, you'll come up with like different constraints. But generally speaking, context depending, you'll figure out what to do if you've got infinitely many. Alright, and with that, that's the exciting world of least squares problems. So now, ax equals b. You can always solve it. You just change your definition of what it means to solve it. Alright, beautiful.